a big inspiration for you?
I'm not sure if yeah, for this specific development, maybe the more spiritual way, yes, okay, is to do something different and something, okay, to try to face the problems in a different way. That you can see that in science fiction a lot of times. But in this case, the origin of Vortex was more simple. In 2002, I was a student and I saw a video of at that moment there not exist YouTube as far as I remember. It's crazy, but I saw a video of the Tacoma Narrow Bridge, and it's a well-known academic example of how some aerodynamical instabilities can work. It was impressive, okay, to see how this structure collapsed, okay, and it was the real origin of the project.
What about the Tacoma Bridge collapse inspired you? Was it the way the bridge moved, or the wind, or what kind of got your wheels turning, do you think?
Yes, because this event is a clear example of how it's a clear example of a problem, okay, and how some aerodynamical instabilities can work. But at that moment, due probably because I was very young, what I saw there was a lot of energy, okay. You can see how this structure made by concrete and steel start to oscillate in a crazy way, and okay, this machine, sorry, this structure that is not a machine, was able to catch all this huge amount of energy. And it's something that, okay, that surprised me. And the idea was, okay, maybe with this physical phenomena, maybe if we try to, instead to avoid, we try to improve, to optimize this phenomena, maybe we can obtain a new technology, a new concept, a new tool to collect this energy in a different way. Probably this technology is not a panacea, okay, it's not the best, but maybe it's different. And if it's different, probably it can cover different gaps that currently are not covered by regular wind turbines.
Yeah. So instead of trying to replace wind turbines, it's what is a different situation in which this might be useful. Can you describe the Vortex Bladeless technology, because it is fascinating to me?
Yes, because in fact in our team in Vortex, all of us admire a lot three-blades machines. Okay, horizontal axis wind turbines is a wonderful technology. They have demonstrated a lot, even probably one of the first technologies that demonstrate that human being is able to produce really, really cheap and clean energy, and we admire that. But also everybody knows that this technology are not perfect in every places, in all applications, and the idea is to try to develop something different, trying to cover the current needs that are in the market.
Can you describe just what a field of these might look like? So our viewers and listeners can kind of conceptualize what we're talking about.
Yes, it's a very simple machine. It's a vertical, slender, and circular section tube or element, okay, that oscillate. Although the idea started from the horizontal bridge, the horizontal structure, in order to collect higher, stronger velocities of the wind, it's better to be slender, okay, to go away from the ground. Trying to look for strongest velocities of the wind, and this structure is very simple. As I say, only vertical, circular, like a pole. Okay, but this technology, the idea and the main goal is to avoid any mechanical elements, any rotating element, any shaft. Okay, the idea is to develop something like a machine that is almost not a machine. Okay, in fact. I remember in 2002, most of people that try to produce energy at home choose photovoltaic panels, of course. Even at that moment, we are not so cheap. Today are wonderful, really, really cheap, but in 2002, it's not really cheap. But I suppose at that moment that was because nobody wants to climb to the roof to put oil or to change parts, okay? Something that you can do with very large wind machines, but nobody, it's impossible a normal family to, okay, it's a huge problem, it's like a huge fence, okay? And the idea is that, okay, may try to develop a new technology as simple as possible, and trying to put on the roof and forget. This is the goal, the original goal.
So essentially, when I look at him, I see just it's like a tall pillar, almost like an obelisk or something like that, that kind of wobbles in the wind. How what's the amplitude of how much they move?
Yes, we can define this amplitude, but it's true. It not rotate, it oscillate. Okay, it oscillate in the perpendicular direction of the wind. Is something that most people expect to oscillate in the same direction of the wind, but it's not. It's perpendicular because the VIV phenomena is a lift forces. Okay, a lift phenomena is not a drag forces. Okay, it allows you to have a more stable movement. In fact, although the machine is very different to a regular wind turbine, it has a lot of analogies with regular ones. Okay, and sometimes even I think that maybe what we are developing is an horizontal axis wind turbine that only rotate a few degrees. Okay, in the currently the angle is more or less 3 degrees. Okay, 3-4 degrees depend of the machine, no more.
Okay.
And it's it, as always in engineering, the technology has advantages and disadvantages, because this very small angle reduce a little bit the swept area that we want to increase as much as possible. But in the other hand, this small angle allow us to avoid any problem with the fatigue of materials. Okay, because we have not any contact element rotating, we have not any gear, any mechanism, but it's true that we have inside the machine one of the key elements that are the carbon fiber rod. This very small angle allow this material to be alive without any crack. Okay, with a lot of decades. Okay.
Interesting. So very much a strategy of install it and never worry about it again, because there's no lubricant, there's no spinning, and the angle's low to minimize fatigue. That's really, really smart. Is there a sweet spot for the size of it and the power output? I saw there were different size ones.
Yes, it's one of that analogies that I mentioned before, because in the same way that regular wind turbines, the dimension affect exponentially to the amount of energy that the machine can work. Okay? This is the origin why the regular wind turbines are growing and are currently huge. Okay, because the swept area grows exponentially, powered by 2. But probably not always the cost grow in the same velocity, and that why the performance, the yield is better. And in our case, happened the same. We have, for example, a very small machine that is almost a toy, the Vortex Nano, okay, that we name. The swept area is very small, and it only is able to charge your mobile phone or to feed with energy LED signalization system, IoT systems. Okay, it's a very, very small amount of energy. But when we start to grow, okay, to Vortex Tacoma, 2 meter high, Vortex Atlantis around 7 meter height. Okay, the power grows exponentially, not only due to the swept area. Also, there is another element, that is the velocity of the wind. That the power that is carried by the wind depend of the velocity, powered by 3. Okay, and you have 2 elements: one powered by 2, the other powered by 3. The higher the better, the bigger the better.
If you don't call it a turbine, what term can we use to describe it?
Yes, in fact, internally we always name these devices a vortex. Okay, this vortex, that vortex. But it's true that when some people start to know these devices and this technology, we have listened all kind of names. Okay, all of them are fantastic. Even Sky Rators, I listen something like that is fantastic. How the people feel that. Yes, probably it's not a turbine. Okay, it's a lift device. It not rotate 360 degrees. I don't know what is it, but it's a machine that collect energy from the wind. That is the main goal.
It does make sense that you'd call it a vortex, because the company is Vortex. How did the company actually found, and do you have any partners in this?
Yes, in fact, the project is started in a different company that is named Deutecno. That company was founded by one very good friend of mine, Raúl Martín, okay, and me, In that company, what we did is mainly we develop PCBs. Okay, we develop electronics for scientist groups or university researchers. Okay, but in Friday's afternoon, let's say, okay, we collect a very small amount of money, and I saw the patent that I wrote when I was a student to my colleague. And he said, okay, what is the percentage of success that you think that have this idea? Imagine that today, I don't know, imagine at that moment. And I said, okay, I don't know, 2%, 3%, I don't know. And he said, okay, go ahead, let's try. And Friday's afternoon, we, as I said,
Wow.
we try we assemble something like a wind channel. We take, we pick a water bottle, okay, we put in the opposite direction with a rod, okay, a steel rod. We put in the wind, and what we saw is that this phenomena is very easy to reproduce, okay. And we say, okay, there is here is something, okay, to start to work. And as I say, in Deutecno we start, let's say 10% of our efforts start to develop this technology, and there started everything. Later we have the support from one of the main oil and gas companies in Spain, named Repsol. They support us during 2 years, fantastic years, okay. And the technology achieved enough maturity, okay, to face first financial round with mainly business angels, okay. And it was the origin of Vortex Bladeless. That is where we can focus 100% of our efforts in developing this technology.
Wow. Yeah, 2 or 3% doesn't feel like great odds, but here we are. What an underdog story.
Yes, step by step. There is a lot of small histories inside, as every development. Yeah.
So what is actually going on inside of these? So the wind blows, it I'm going to say wiggles, but it moves perpendicular to the wind, the leaf effect. I have to assume there's some magnets and coils inside. What does that architecture look like?
Yes, exactly. What we have is a hollow tube, very light, very rigid. Okay, this is what we name the mast, and that mast is supported by a carbon fiber rod. That is the element where we try to concentrate all the flexion. Okay, and more or less in the middle there is an alternator that, of course, is based in the same physical phenomenon that all alternators in Faraday law. Okay, there is permanent magnets and coils exactly like that, and it transforms the movement into electricity in an altered current. Okay, it's a crazy altered current because it's the amplitude, the frequency, everything is not useful. This wave, and we transform to DC. Okay, we transfer to DC current. Okay, we use this how it's named. Okay, we transfer to DC with diodes. Okay, and that's all. It's very simple. But it's true also that the a rectifier. Sorry, in English. Sorry, I apologize. And just and this alternator it's not only in charge to produce energy, to transform the mechanical energy into electricity. Also, we use this element to synchronize, to tuning, okay, the machine to different velocities of the wind. Because what happened in our machine is that two frequencies are close in order to achieve the resonance. Okay, in one side is the structural natural frequency of the machine, and in the other side is the frequency of the vortices. When both frequencies are close is where the resonant appear. Resonant is always a very good way to transmit energy from a fluid to a structure. And this frequency of the vortices depend also about the velocity of the wind. And of course we have not any control about the velocity of the wind. And what we do with the alternator is to modify a little bit, that we try to modify the frequency of this structure in order to increase what is named the lock-in range, okay, the range of velocities of the wind where that structure is resonating, okay, is moving by the wind.
How do you tune the structure itself with the alternator? Does it change like electromagnetic strength, or what does that tuning look like?
This is very simple. It's a passive way, okay? When you try to estimate the frequency of oscillation of one structure, you have to keep in mind the mass and also the strength, okay, the rigidity of the structure. Okay, this is a linear, okay, this is a constant of rigidity. This is constant, as I say. And what we do is to you introduce permanent magnets by repulsion. That the behavior of that permanent magnets are more or less like a spring, but it's not linear. Okay, it's more exponential. At the end of the day, what we have is when the velocity of the wind is low, the amplitude is also small, and mainly who define the frequency of the structure is the carbon fiber rod. But when the velocity of the wind increase, this amplitude also increase, and there start to affect also these permanent magnets by repulsion. We have something like a constant of elasticity of the structure, and also we add a magnetic constant, okay? And which means that we increase this K, okay? And we can increase in this way the frequency. It's a very, very passive way. We have not to introduce any actuator, any rotating element, okay? And also the same magnets that are what we use to produce energy.
It's very clever. It's very clever design.
It's a little bit crazy, but it works.
You know, if it works, it's not crazy. It's only crazy if it doesn't work, I think. You already mentioned it's not going to replace wind turbines. It's going to be other situations. Can you describe a couple of the cases where a vortex makes more sense than a turbine and where you kind of envision it in the future?
Yes, you are right. The idea is not to replace the regular ones, that maybe in the future can happen or not. But our main goal is to, every day a lot of energy go through our roofs, and nobody are taking advantage of that. Okay, and currently is fantastic because there's photovoltaic panels. It's a fantastic tool and it's useful for a family to collect their own energy. Okay, it's great. But as everybody knows, in the night or in winter sometimes, okay, you have not enough sun. Okay, and one of the best applications is to use in a regular home, a small home for families, hybridized with photovoltaic panels. Statistically, in the night it is more windy than in the day. Also statistically happen the same between the winter and the summer. Both energy sources are fantastic to mix, okay, and they increase. It's something like a synergetic combination, and probably is our main goal. Okay, it's a small machine that produce a small part of the complete amount of energy that a family needs, but probably in one of the most important moments, for example, to feed with energy a refrigerator, small lights, okay, these kind of things. And another application, for example, what we see in a lot of antennas, okay, are currently feeding with fuel. It's crazy, but it's happening. And although some of them are replacing by photovoltaic panels, here happen the same. The batteries always are not able to maintain to storage all the energy that the system needs, and maybe if we mix wind and sun, maybe we can a better performance.
Yeah, one of the challenges with solar is, you know, we the duck curve, they like to call it, where you have a lot of power at certain parts of the day, but that's not necessarily when you want to use all the power. So supplementing that makes a lot of sense. How big of a mast, if I'm putting one of these on my roof next to some photovoltaic, solar panels, how big is this going to be?
What we have in mind, at least, is what we name Vortex Tacoma, a machine between 2 or 3 meters, okay, depend more or less.
Okay.
Less than 10 kilograms, okay, it's a very, very light element.
Oh.
And with that, the idea, each Vortex Tacoma, our goal is to produce around 100 watts of nominal power. 100 watts, we know that is not a lot. But the idea is to produce the cheapest 100 watts from the wind, okay, in the world. This is our idea and our goal. And you can put 1 or 2 of these devices with your 5-7 photovoltaic panels, and together the idea is to have a better facility to produce energy.
That was my next question, was how much power are you actually getting out of this? So 100 watts for 10 kilograms feels pretty good. How do the, right now, or I guess in a future state where you're doing production runs of these, how does the cost compare to solar panels per watt or to traditional turbines per watt?
Yes, in Spain, where we are, you know that we have also a wonderful sun and also a very clear atmosphere. Here the photovoltaic panels are working very, very good, and the levelized cost of electricity is impressive. Okay, for example, yesterday in Spain, some people pay to produce energy, okay, because we have a lot of energy in during the day. Okay, and sorry, the question. Sorry, the idea fly from my mind. Sorry, could you repeat?
No, you're fine. The question was, how does it compare to photovoltaic, and how does it compare to traditional turbines? Cost per watt.
Yes. For example, as I said before, in Spain, the performance of photovoltaic panels is great, and it's not easy to produce cheaper energy from the wind with small wind machines. It's more easy with very large machines, but it's not easy with small machines. But it's true that if we compare our machines, the Vortex machines, with regular wind turbines, small ones, okay, there are a lot of room to improve. Okay, the current levelized cost of electricity of very small machines, vertical axis, horizontal axis. Okay, there is even 10 times, 20 times bigger the cost of that devices, and in our estimations we think that we can reduce around 40% the cost of the electricity if we compare a Vortex machine with a regular one with the same dimension, with the same nominal power.
40% is significant.
Yes, but if we speak with small devices, okay, when we speak about large devices, the challenge is huge, okay, their performance are incredible, okay. Let's see what happens. It's not a reality today, okay, we are maturing the technology, the economy of scale will say, okay, what happened, but this is the goal. Our preliminary numbers say that it's achievable. Let's see.
How do people respond when they see these systems and when they hear about them in the first place? And how do you kind of explain it to them so that they understand it?
In general, it's a very, okay, this technology has a very, very warm reception, okay, from most of people. In fact, we enjoy that every day because although we are a very small team, now currently we are only 5 workers, we enjoy the support from hundreds of people every day, working, trying to transform this idea in reality, supporting us and helping us in a lot of ways. Okay, you can't imagine, it's impressive. In fact, we know that we are not able to take advantage of all this support like it deserves. Okay, it's impossible to take advantage of all the people that are trying to. Okay, I love the idea. We have to transform this in a real product. In general, it's very good. Okay, in general, we can't be more happy about that.
That must be very encouraging to see it taking flight.
Yeah, it is.
Keynote speakers and live sessions for EE Power Day are brought to you by Mouser Electronics. As your design fulfillment distributor, Mouser is your authorized source for millions of components from over 1,200 leading brands. Come discover, design, develop.
You mentioned a couple applications earlier, but I'd like to dig into a little more how these might be used. We talked about putting them on a house. Are there other ideal applications where you think this is just a winner of a concept?
For small applications, that two probably are the main ones. Okay, urban residential environments, and also isolated areas where you need a small amount of energy. If you increase the dimension of the device, for example, Vortex Atlantis, that can be our next stage, is a machines of around 7 to 10 meter height. These devices, our goal is to produce around 2-3 kilowatts, okay, with that. And what we see with these devices, and even with bigger devices, is that the offshore environment or the ports and those areas that are close to the water, can be perfect for these devices. The lack of steel mechanisms, the lack of those elements that can be degraded by humidity, salt, and corrosion, maybe can transform this technology in a good option to work in that areas, okay, in the harbors, in the ocean, in the ports, in this environment.
Yeah, let's talk about materials a little bit. Just a couple dozen miles down the road here, they make the large wind turbines. So we see like single turbine blades on train cars going by all the time, and they're massive, and they have to be so strong because they're so big. What sort of materials are you using to develop these?
The reality is that with Vortex Tacoma and Vortex Atlantis, the 2 meter to 10 meter devices, until today we are using the same materials that regular wind turbines. It's true that we are trying day by day to reduce the amount of this material, okay, the kilograms of these materials, not only due to the costs or the environmental aspects that are important, also because the aerodynamical performance of this device increase when you are working with very, very light device, okay? It's useful for you to increase the aerodynamical performance and also the range of velocities of the wind where you are able to maintain that resonance. With very, very small devices, sometimes we use different materials. We use more plastics, not the same. We are not using the same level of composite materials. And in the case of the plastics, even we for example, in the last pre-series that we manufacture of Vortex Nano, we use PET. In fact, we manufacture bottles of water without water, with the shape of our mast, okay? And we saw, for example, with the ultraviolet radiation works very good. It's impressive how good it's working. But in general, we will use probably similar materials that regular wind turbines.
Okay. Yeah, I think I have a spool of PETG over here off camera. Some good material. So 3D printing, has that been helpful for you to like rapidly prototype and innovate, or is it more, small scale, small batch type production is why it's useful?
Yes, absolutely. Okay, the 3D printing for us is you have to think that mostly we are making mistakes every day. Okay, and that mistake has to be as cheap as possible. and of course, yes, we are using 3D printing. It's impressive because year by year we are seeing new materials that are better for our devices but it's true also that we are trying to be close to the industry, to the regular manufacturing processes, okay, blow molding, molds, injection, these kind of things, because at the end of the day, when we manufacture in Syria, probably, this is the way. Let's see. Just 3D printing for sure is one of the key technologies for us if we are able finally to obtain the success.
You mentioned you've made a lot of mistakes. Is there a mistake you can share that you've learned from? Maybe one that you thought was a great way of doing something, but it was just a surprise and didn't quite work out and you had to adapt?
Wow, a lot of them. Some of them horrible ones. For example, at the beginning we didn't take into account how important is the damping of the materials that we are using. And if you forget that aspect, and you are only thinking about fluid dynamics, probably what you obtain is a machine with a huge diameter, okay, not so slender, just the opposite, okay, and because if you are only, as I say, you are only taking into account the aerodynamics, the swept area, okay, grow, and okay, I remember that we developed some machines with this idea. Even I remember one of 4 meter height. And yes, the material at the bottom crack and drop, and okay, so we have a beautiful video about that.
How have you changed your designs as a result of these failures? Have you changed reinforcements or shapes, things like that?
Yes, although the original idea is more or less similar in about slender elements, circular, and these aspects are the same. It's true that every day we are manufacturing these devices lighter and lighter, okay, with less amount of material. It's true, for example, that currently we are also playing with more natural materials. Balsa wood, for example, that if you compare the density and the strength of some natural materials, you can see that are really close to, for example, carbon fiber. Okay, it's impressive how the nature is able to develop these wonderful materials, and we are trying to introduce that because it's true that the performance that we saw is better. And let's see. As I say, in general, the device every day is more slender and more light. Okay, it's the more general evolution of this development.
You mentioned earlier fluid dynamics. My understanding is that fluid dynamics is very difficult to simulate. How hard is this to actually simulate as you go to design these things, and how much of it is just field data that you extrapolate from?
It's true, and we understand that directly, okay? Because at the beginning we try to simulate 3D simulations, 3D models, okay, with all the VIV phenomena, everything. We try to include everything in the simulation, and soon, happily soon, we saw that we need probably a computer that today not exists, and to have the complete behavior of the device. And how we face that is we named that a 2.5 dimensional approach. Okay, that is not 3D, it's not 2D, it's something like in the middle. And with that we started to have some solutions, but also another very important thing is to contrast that results with the reality every day, and to close the loop and feed with the real results your simulations, and every day you have to do that, because if not, if you only trust the simulations, when you go to the reality you will see that you are far from the reality. Yeah.
When you go to reduce weight, I imagine materials for the tower, there's some mechanical engineering you can do there to reduce that weight, but an alternator, the nature of magnets and wire cabling and just current draw and current generation automatically creates weight. How does the alternator impact the performance?
Yes, it's our biggest challenge during the last 2 years. Okay, how to reduce the power density of our alternator. And you are right, the copper, the neodymium, all these elements, the silicon steel, the weight is huge. Okay, it's not easy. It's true that the stator is not something that affects the aerodynamics when I speak about the weight. Okay, and also how we try to face this challenge is because when I say weight, it's true that more specifically we have to say inertia. Okay, and is this inertia what we have to reduce? What we do is to drop a little bit, we put a little bit down that alternator, but we have also a limit, it's a consensus of everything. And also we are playing with electronic things, okay, in order to reduce this weight. Okay, at the end of the day, this system is very simple, but this simplicity is probably the biggest challenge. Everything is very close with everything. All parts are affecting all parts, and how to balance all of them is the biggest challenge, and also the most beautiful thing of our work.
So when I think about the alternator and how it is probably arrayed in here, you have the tower coming up and you have a pole in the middle, and the tower shakes around the pole. That's correct?
Exactly. That pole, like a tower, okay, that is in the middle, is the element that, let's say, introduce the ground, the static element, inside our mast. And this is our stator. And the rotor, that we have not a rotor, joking we say oscillator, and we name every day oscillator, okay, no rotor. That oscillator is the element that we are trying to reduce the weight. This alternator has a radial symmetry, okay, because the idea is no matter from where came the wind, the machine always has to be in the same position, okay, and the alternator has to work exactly equal no matter where the direction of the wind came.
So the center pole can be heavy, so you can make a very heavy stator as long as the rest of it is lighter. That makes sense. What are some of the biggest hurdles that you face today in terms of scaling and growing and the adoption of this technology?
Yes, now we are focused because the technologies started to be more or less mature when we speak about very, very small machines, okay? We have to go step by step. And our main goal now is to be close to the industry in some way. Because there is a lot of guys with a lot of knowledge how to manufacture things very high quality, very cheap, okay, very what we need. At the end of the day, we are a small research team, okay, and we have to introduce all this knowledge in the project in some way. And now we are trying to start to increase our minimum viable products, our pre-series, okay, in order to reduce the cost of that machines, okay. It's true that currently our clients are not focused in the levelized cost of electricity in dollars per watt, okay, are not focused exactly only about that. It's important, but it's not the unique goal. But it's something that sooner or later will happen, okay. We have to reduce the cost, and our main challenge today is to reduce that cost.
I know with traditional turbines, like birds have a problem with them. They're just so big. I don't know that there's like they quite know how to handle it. Is that an issue with these? I have to assume not.
I mentioned before that there is a lot of people that are trying to support us in different ways. One of the main ones probably are Sea Over Life. It's a huge group of lovers of birds, and we have tested some of our devices even in their facilities, and until today they think that our device is more friendly with birds, okay, and okay, it's one of the strengths of the technology. Or we have also weaknesses, but for sure it's one of the strengths. For example, in Spain, most of the areas of windy areas are currently we have wind turbines, okay, in our country. But still there is some places, very windy places, with a wonderful wind resource that we are not using here because there are birds, okay. If we can develop this technology in larger scale, and maybe can be a solution to combine the birds and the wind industry together without problems. It's impossible to develop something that not affect at all the nature. It's impossible, but maybe, okay, we can combine different solutions in different places.
You've talked about scaling and that you're at a point where you're starting to hope to scale. When people go to evaluate these systems, when people go to decide, do I install turbines, do I install vortexes, what sort of trade-offs and decisions and what sort of metrics do they actually care about, and how does Vortex speak to those?
Yes, if you need a huge amount of energy, and if you need enough ground area to put your devices, and if you need also financial things, a technology that currently have demonstrated something, okay, of course Vortex is not the solution, okay. Currently technology is, as I mentioned before, is wonderful. Our idea is that, okay, is the reality is that it's not easy to see a windmill on the roofs of the people. There are some, but it's not a solution that covers all the needs. These small applications have to be our first step. Our financial estimations, that at the end of the day is very, very important. We keep in mind the capex, okay, the cost of the machine, and of course the OPEX, the operative and maintaining cost mainly. The capex, okay, the idea is the machine is very simple. The machine is also circular. Probably one of the problems that face the small wind turbines is that it's not so easy to automatize the manufacture of these devices, mostly when they are using composite materials. But it's true that currently exist industrial solutions, filament winding, a lot of solutions to automatize that manufacturing processes. Maybe this different machine can be easier to automatize, okay, and maybe that can affect the final cost of the machine. This is in one side, in the capex. About the OPEX, about the operative and maintenance, it was the original idea. Okay, simplify the system and reduce as far as possible the need of replacement of any part, okay? And there is where we feel more strength, okay? Because the idea is that you put the device on the roof and you forget. This is the main goal.
I can picture the early stages of this, of teams just having to wind these by hand. Has that been automated yet, or what does that process look like?
Yes, currently what we do is we contact with close manufacturers, close in our area, okay, and they are manufacturing the different parts, okay. Some of them with plastics, composites, or even the alternator. That probably we are working more directly, but also there are some companies that are supporting us to manufacture these alternators. And what we are doing at home is assemble. Okay, in our facilities we assemble these devices, but not forget that we are speaking about a small series. Okay, and let's see in the future how we can increase this volume of devices.
Yeah, I imagine lots of different manufacturing techniques to make these viable. Where do you hope this technology will be in the next 10 or 15 years?
Well, it's okay. The dream and the goal is to provide to the families a new solution. The photovoltaic panels is wonderful. It probably provides more than a half of the final needs, okay? But also the families need to be able to produce their own energy. And even not only that, not only produce their own energy, maybe they have to increase their role in the market, okay, to be also providers, not only distribute energy, also we are speaking about decentralized energy. That I think that is the next step. It should be great if, as you say, in 10 years, this technology or also others are disseminated and are working in that direction, because the energy solution came from the integration of different solutions.
Yeah, it's an exciting idea to think about. You know, solar power, I feel, is pretty residentially viable, but to make wind power residentially viable is a very exciting concept to me, personally.
Yes, it's a win-win, this mixture, I think, yes.
Win-win, wind. You could use that later. What are some of the important learnings as you've started to ramp up this new and novel technology? What are some learnings you could share with other entrepreneurs who are working on, similar types of challenges? Not wind power, but novel new technologies that's maybe not understood by the market yet.
I think that one of the things that are helping us a lot is to try to simplify as much as possible. Okay, it's through that idea that there is a lot of engineers working, trying to optimize a part that maybe is not necessary, okay? And this concept, I think that is great. And as far as it's true that some engineers love, okay, and we love to introduce some new things, try to improve a little bit more, but at the end of the day, the simplicity is something beautiful, and even more important, it works better. And you reduce the statistics of the problems, okay? And I think that is probably one very good learning that we have obtained during these years.
Simplification and elegance over complexity makes a lot of sense.
Exactly.
You mentioned early on you read a lot of books, you read a lot of sci-fi. Do you have any favorite either classic sci-fi books or modern sci-fi books that you've been enjoying lately?
A lot, but probably Isaac Asimov was one are the roots of my love for the science fiction. Okay, and yes, this we have to create the future together. Okay, and all of us, I think, that can give something to obtain that.
What a great sentiment to end on. I think we are out of time, but thank you so much for being here today. This was fantastic.
Thank you, Daniel. A real pleasure. Thank you very much for this opportunity, and thank you.
Again, that was David Yáñez, co-founder, president, and CTO of Vortex Bladeless. I've never really thought about wind generation without blades and turbines before. I hope you all found that as interesting as I did. I know I'll definitely be keeping my eyes peeled for one of those out in the wild. Up next, we have 2 more live sessions. The first is with Infineon to explore the impact of wide bandgap semiconductors on power conversion stages for photovoltaics and energy storage systems. And after that, we have a session with onsemi digging into DC fast charging. They'll cover the latest megawatt charging standard. They'll dig into key topologies like Vienna rectifiers and the T-type neutral point clamped converters and some silicon carbide solutions and a lot more. So go check out those sessions. And after those, I'll be back for another keynote with the CEO of Zendi. It also looks like we have a few minutes before our next live session starts, so now would be a perfect time to go check out the digital exhibitor booths. Thanks for tuning in to this session of EE Power Day, sponsored by Mouser Electronics. I'm Daniel Bogdanoff, and I'll see you back here in about 2 hours.